From the cold, infinite expanse of the primordial cosmos, born in a microscopic crucible of unimaginable energy. All right, let's bring it right back down to Earth. Hi, I'm Katerina. Today, we're going on a wild journey that spans literally from the absolute limits of the observable universe straight to, well, your kitchen counter. And we're going to do it by focusing on the absolute integrity of our scientific models.
So I've got to pose this question directly to you. What on earth does the rapid expansion of the early universe have in common with a cheap can of lager? I know, it sounds like the setup to a bad joke, but I promise you it's rigorously grounded in science. Our unifying theme today is expansion, how the exact same physics of pushing matter apart dictates both the shape of the cosmos and, believe it or not, the texture of our food. Section 1. Redefining the Big Bang and busting some outdated myths.
You know, there's actually a massive contrast between those textbook diagrams we all saw in the 1980s and our modern cosmological models. For decades, we were all told the universe exploded from an infinitely small, dense point, a singularity, right? Well, scratch that. Cosmologists actually threw that idea out 40 years ago. The modern, rigorously fact-checked model shows that roughly 13.8 billion years ago, pure space, containing literally zero matter but packed with inherent energy, expanded exponentially in a process we call inflation. Basically, space doubled and redoubled until it was completely flat. And it's only when that crazy inflation stopped that the inherent energy converted into matter and radiation. That conversion? That is what we actually call the hot Big Bang.
So, after that initial inflation stopped, space just kept on expanding, allowing things to cool down and finally clump together. Just one tiny microsecond after the hot Big Bang, quarks condensed to create protons and neutrons. But get this, it took 379,000 years for things to cool enough for electrons to be captured to form stable atoms. At that exact moment, light stopped bouncing off free electrons and just flew free across space. We can actually still see this ancient light today. And then gravity took the wheel, pulling matter into clumps until, roughly 100 million years later, nuclear fusion ignited the very first stars.
Now, that primordial light from 379,000 years after the Big Bang, we call that the cosmic microwave background, or CMB for short. And it defines a very specific absolute number for us, 46.5 billion. Because the universe is constantly expanding, 46.5 billion light-years is the exact strict radius of our observable universe. The CMB is literally the absolute limit of the light we can detect. So any information from beyond that boundary, it simply does not exist in our universe. Wild, right?
Moving on to Section 2, an inventory of space, exploring the engines of the cosmos.
When we take a cosmic inventory, it turns out a star's size strictly dictates its destiny. Take red dwarfs. They're the smallest, but because they burn their fuel so incredibly slowly, they're going to live for thousands of billions of years. Then you have yellow dwarfs, like our very own sun, living a comfortable, steady 4 to 17 billion years. But then, look at the blue giants. These things are incredibly massive, up to 250 times the radius of our sun. But because they're so huge, they burn through their fuel incredibly fast. They only exist for a few thousand million years before spectacularly dying out.
But how exactly do they end? Well, despite the terrifying, dramatic black holes that we constantly see in sci-fi movies, they are actually incredibly rare. In reality, over 97% of all stars in the universe will quietly end their lives as dense, slowly cooling white dwarfs. Imagine taking roughly the mass of the entire sun and packing it into a sphere the size of the Earth, just glowing gently from residual heat. That's a white dwarf. But for that remaining 3%, the truly massive stars, the physics gets completely mind-bending. If a star is massive, but not quite massive enough to form a black hole, it collapses into a neutron star. The gravity here is so insanely strong that it literally overcomes the ability of electrons to keep atoms apart. Electrons and protons are just crushed together into a dense ball of pure neutrons. To put that into perspective, a single sugar cube-sized piece of a neutron star weighs as much as Mount Everest. I mean, there's no way to even fathom that kind of weight. It is the absolute ultimate extreme of matter compression.
Section 3. Cosmic Mysteries. Let's talk about what we simply don't know. Okay, prepare yourselves for this one. 85%. That is the percentage of matter in the universe that is completely, utterly invisible to us. We call it dark matter. Now, we know for a fact it exists because without its extra gravitational pull, spinning galaxies would just fly apart into the void. But it doesn't interact with light, it doesn't interact with ordinary matter, nothing. Our best guess right now is some undiscovered subatomic particle. But honestly, as of today, 85% of the universe's mass is a total ghost.
And the cosmic anomalies certainly don't stop there. We observe galaxies accelerating away from us, pushed by a mysterious anti-gravity force we've dubbed dark energy, which, by the way, makes up 68% of the total energy in the universe. We also see these fast radio bursts, these incredibly short pulses generating as much energy in a single millisecond as the sun does in 80 years, and some of them mysteriously repeat from the exact same source. We have incredible, rock-solid data on these phenomena, but absolutely zero explanation for them. It's a giant puzzle we're still trying to piece together.
All right, sharp pivot to Section 4, the perfect bread recipe and the physics of microexpansion.
I absolutely love this quote. The easiest way to make delicious bread that gives you the maximum flavor for the least amount of effort. Because here's the thing, we are trading backbreaking physical labor for precise chemical ratios and ample time. What we're looking at is a highly tested, strictly scientific baking method. Sure, you have your standard flour, salt, and yeast, but the real scientific hack here, it's the inclusion of 1 tablespoon of white vinegar and half a cup of cheap lager. Now, you do not want a fancy, flavorful craft beer for this. A cheap, light lager combined with the acid of the white vinegar instantly mimics the complex, fermented flavor profile of a traditional sourdough starter. And the best part, you get that flavor without having to maintain a starter for weeks on end.
So, step 1 is absolutely crucial. You mix it into a shaggy ball, and then you do nothing. Literally nothing. You let it rest for 8 to 18 hours. This is exactly where the physics of expansion takes over. That long rest allows the flour to fully absorb the moisture, and the yeast slowly releases gases, expanding the dough. After that, you do a quick shaping, forming a boule by creating surface tension. Prove it for 2 hours, and then it's time for the final heat transfer.
Now, this step is pure thermodynamics. You put a heavy Dutch oven into your standard kitchen oven and crank it all the way up to 500 degrees Fahrenheit. The goal is to absorb as much heat energy as physically possible. Then, when you drop the dough in and immediately lower the temperature to 425 degrees, your Dutch oven acts like a terrestrial thermodynamics chamber. It traps the steam evaporating from the dough, keeping the surface perfectly gelatinous just long enough for the bread to expand fully, right before it crisps into the absolute ultimate crust. I want you to really think about this for a second. In the early universe, inherent cosmic energy and inflation physically pushed the fabric of space apart, essentially creating the vast canvas for all our galaxies. Meanwhile, right inside your mixing bowl, the biological energy of the yeast and the carbonation of that cheap lager release gases that push a microscopic web of gluten apart, creating the crumb of a perfect loaf of bread. The exact same mechanics of expansion are dictating the structure of both our massive universe and our everyday food. So the crucial takeaway today is this. Science isn't just some abstract concept that only happens in million-dollar telescopes or massive particle colliders. From the 13.8 billion-year expansion of infinite space to the 20-hour rise of a loaf of bread, the exact same rules of physics and chemistry apply everywhere. So it really makes you wonder, what other grand cosmic rules are dictating the chemistry hiding right there in your very own kitchen cabinets? I'm Katerina, and I hope this cosmic journey left you hungry to find out. Thanks so much for exploring with me.